Hi, welcome to the 8th class session of Points of Topology 2 course at BTL. This is Shovik. Uh, I'm a research scholar of IDA Madras, third year, under Dr. Maskasi. So, before starting or before going further, let me know that
Sir?
whether I'm audible and is the screen visible to you or not. First, let me confirm.
Hello, sir.
Yeah, hi, Mr. Can you please confirm whether my screen is visible and am I audible?
Uh, yes, it is audible.
Okay, and the screen is visible to you?
It is audible.
Okay, thank you, Mr.
I have
Okay,
a
so
question.
yeah, yeah, tell me.
Why R with lower limit topology is Linear law?
Well, hold on a minute, please. R is lower limit topology. Give me.
मुझे दे दिया उसे.
Well, so okay, in the last session we have done the proof of this fact. Anyway, but we can today let's try to again prove this thing. Okay, so the proof is um, quite lengthy. So let's see. The question is what? So the question is R is lower limit topology is lambda. So the proof is quite tricky. Directly we are not able to prove this. Okay, so we prove it via some different technique. Okay, so let's see the proof. So showing R with lower limit topology lambda is equivalent to show that every open covering of RL by base elements contains countable subcollection. Sorry, let me make it small. Subcollection covering RL. Every open covering of RL by open cover of basis elements contains a countable subcover. Okay, this is what we need to prove. Okay, so start with the countable subcover. So let A is equal to yeah. So I mean it start with the cover containing all the base elements. A alpha, B alpha, alpha belongs to G, B and open cover of RL. Okay. Now what do I do? When we take we are defining C to be union of A alpha, B alpha, alpha belongs to J. The subset of R. So first we are going to show that R minus C is countable. How to show this? Let X belongs to R minus. So we know that X does not belong to no open interval of the form A alpha B alpha. So X belongs to A beta for some beta. Now choose such a beta and then choose Qx to be a rational number belonging to the interval A alpha B alpha. Sorry, A beta B beta. So that means what we're going to do? First, we take a x, and we are saying, I mean, then we are observing that x is what? That x is equal to A beta for some beta. Now, mm, Qx be a rational number. We are taking Qx be a rational number belonging to A beta B beta. Okay. Now, as A beta B beta is contained in C, so is the interval Qx is equal to. It follows that if x and y are 2 points are mine in the complement C and with x not equal to y, specifically actually with x less than y, then Qx less than Qy. Okay. Why? Otherwise, x less than y less than Qy less than equal to Qx. This implies y will lie belongs to x and Qx, and hence y belongs to C. But there is a contradiction. So only this situation is possible. Okay. So therefore the association x goes to qx from where to where from r minus c to q is exactly. So r minus c is countable. Okay. Now so this tells that r minus c is countable. This is one thing. Okay. Now the next step. Now here we will show. Here we shall show that countable subcollection A covers R with low limit to polar. So, and here the trick follows. To begin with, choose How we will do? For each element of R minus C, there exists an element of A containing it. So, and this gives a countable, this gives countable subcollection of A or R minus C, call it A dash. Now, the main trick. Here is the main trick. What is that? Main trick is that topologize C as a subspace of R, and in this topology, C satisfies the second counter axiom. Now, C is covered by the sets A alpha, B alpha, which are open in R and open in C. So, then, of course, some countable subcollection covers. Suppose this subcollection consists of the elements A alpha, B alpha, alpha equal to alpha 1, alpha 2, total. Then the collection A double prime is equal to A alpha, B alpha with alpha is equal to alpha 1, alpha 2, total is a countable subcollection of A that covers the set C and A dash union A level dash, the countable subcollection of A that covers RL. towards R. Okay. So what? So this tells R with low element topology is linear. So this is the proof that. Okay. So Mustaq, this is the proof of the fact that R with low element topology is
Yeah, I understand.
so tell me, okay, it's good. Okay, so do you have any more question or doubt? Okay, I hope this problem is clear. Okay, now let's uh, start with um, the assignment problems. Okay, so let's start with the objective assignment problem. So what is the first question? The first question is that let V be a normed space. Let V be a normed space, and given T belongs to B or V, there exists an operator expt belongs to B or V such that expt is equal to summation 0 to infinity to the power n by factorial n. So now think about and tell me how to solve this or attain this problem. So what is the data given? V is a normed space and we have a bounded linear operator T over V. Now we need to show that there exists and some operator which is also bounded a linear such that the operator is equal to summation 0 to infinity to the factorial n. So of course, okay, first think about it. Or well, let me give some hint. Since so we have already seen that for in the Banach space and in the bounded linear operator, this fact is true. But here V is given to a normed space, but V is not given to a Banach space, right? So try to show that. Also, so obviously one might guess this is false. But now you need to provide a counter example to show this is false. So think about it and try to provide a counter example showing that this statement is a false. So let me mm, what are the counterexample? So answer is false. Why? So choose V to be the following state. Although sequence L1 x such that xk equal to 0 except for finitely many k. Okay, and put t from V to V be the shift operator. That is P of Ei is equal to Pi plus 1. Then t to the power n factorial n E1. This thing does not make sense in V. Okay, kindly hold a minute. Let me close the meeting and let me rejoin. Okay. Hello, anybody? Can you please confirm have the order audible? I hope. Sorry, I put that wrong one. Oh well, sorry for the inconvenience. Due to some issue, my the Google Meet along with um, the Google Meet along with screen sharing was not working. That's why I had to restart then again. Okay. Well, sorry for the inconvenience. So now let's get back to our original question. Um, what- uh, well, so let's get back to the original question. So this question here, what we need to show. Hmm. Mm, so so here we need to show that. Okay, let's start from the beginning. So the question was that suppose V is a normal space and suppose T belongs to the boundary linear operator V. Now we need to show does there. Now the question is that there exists an operator exponential of T which is boundary linear, so that exponential of T is equal to exponential of T is equal to summation 0 to infinity to 1 factorial. Okay. Now answer is false. Why? Observe that the same statement is true, but when the case V is a Banach space, for any Banach space, any boundary linear operator can be written in the form. But in general, if you know Banach space, this cannot be true. So what is the counter example? Choose V is equal to Xn, so the Xk is equal to X of finally many k, then put T V to be the shift operator. And T of Ei is Ei plus 1, then summation 0 to infinity to the power factorial n, this thing does not make sense in V. So exponential of T, such a thing, not possible. Okay, so these arguments. Okay, now so this question is over. Now go to the next second question. So now question is, let V be a Banach space, then given T comma S belongs to B of the boundary operator, we have exponential of T plus S, exponential of T compose exponential of S, where exponential T is repeated over n by factorial n. So tell me how to solve it. So exponential T is some function. Now I want to show this true or false. Okay. So for that we need to use some property of exponential function. At least if we use some property of exponential function, we can see that this is certainly not the case. But to answer the completely whether true or false, what we need to do, we need to provide a counter example. So think about it, which counter of which example should work. So firstly, consider two such uh, first consider two such operators. Well, so so the answer is false. Okay, and so what we counter was to put v is equal to r2 and boundary linear forms with the matrix form and put p is equal to 1 0 0 0, x is equal to 0 1 0 0. Then expt is equal to exp1 0 1 and exps is equal to 1 1 0 1, for which here our t is equal to, okay, sorry, the t is there. So these are corresponding exponentials. Now we have what t plus s is equal to 1 1 0 0. So exp t plus s is equal to exp1 0 1 exp1 minus 1. So exp t plus s is not equal to exp t compose exps. Okay, and note that note claim is true only when t and s commute. Okay, well, now go to the next question. Let V be a Banach space. Given T belongs to V, exponential T is an invertible operator. So of course one may guess that this is not possible. I mean this is not true, obviously. So now how you can prove that this is indeed not true? Technically, basically, you have to provide a counterexample in order to show this is not true. So think about it and let me know which counterexample you can provide in order to show this is not the case. Well, so one might guess this is not true in general. So what is the counterexample? The counterexample is as follows. So it is true, and if we conclude that if Tx is equal to St, the exponential of T plus h is equal to exponential of T compose exponential of S. And now we have exponential of T compose exponential of minus T is equal to exponential of 0, which is ident, which is equal to exponential of T. So this tells that exponential of T is an invertible operator. Right. So now question number 4. I mean, the previous question is basically exponential of T composed of minus T is equal to ident. So that's fine, whatever. Let V be a normal index by NLS, and let T is a bounded linear operator on V. Define F. The collection outside a boundary linear operator is a boundary by T goes to T square. Okay. Now question is, which one of the following correct? First one, F is not differentiable at 0. Second one, F is differentiable with df of t is linear map to t. Third one, F is differentiable and df t till th plus ht. And the fourth one is F is continuous linear operator. So, so look, so you have seen that in differential topology there is a maps like x goes to x square, okay, which is a forward differential. But this happens in real time. But here we have a nominal space, okay. Now in this situation, you need to understand whether this one is true or false, correct, or which one is true. So the answer is C and D is true. How to do? Limit h goes to 0, t plus h whole square minus t square minus t h plus ht by norm of h. This thing is equal to what? This thing in limit h goes to 0, h square by norm h. This thing is equal to 0. So this implies what? The derivative of f at t of h, this is nothing but dh plus th. And of course, and so f is continuous. So so C and D are true. So of course the rest two options are false. Okay. So that's the argument. Now the fifth question. There exists a norm on, that is the polynomials over R, such that P is a Banach space with this norm. How to do this? Or is it actually true? So basically it is saying that on the set of polynomials is there is usually degree norm. But this tells that we can give some, is it possible to give some other norm with respect to which the P becomes Banach space? So that is the question. So, of course, it seems to be not true. So, answer is false. So, this P of R is nothing but union of R of R, degree n polynomials. Okay. So, degree n polynomials. And each of them are finite dimension. So, complete with any norm. And they are closed in P of R in P R with this. Now, in the subspaces P and R nowhere dense, P plus P is the countable union of closed and nowhere dense subspace under any norm, and hence is of first category. So then the bare category theorem tells it cannot be a complete metric space. So let me re-explain. One. So P of R is finite dimension. Now the question is that is it possible to put a norm on this set of real polynomials with respect to which this collection becomes a Banach space? Now the certainly this is false. The how this can be done? We can write this set of polynomials. Can it is literally the degree linear degree and polynomials. Okay, which are finite dimension, hence complete and closed in P. Okay. Now, being a proper closed subspace, each P and nowhere dense in P, and so P is the countable union of closed and nowhere dense subspace under any norm, and hence the first category. And by bare category theorem, it tells that it cannot be a complete metric space. So this is the argument. Okay. Okay, there is really very nothing. There is really nothing complicated to do. Okay. Oh well. Now question number 6. Consider a with R what given by xy going to so y square minus 1 and h of xy going to x square minus y square. Okay, 1 minute. Okay. So now the question is which one state true or false. Here exists a continuous function g from R to R such that x comma gx equal to 0. Here is the continuous function g from minus 1 comma 1 to R such that f of x comma 0 for all x belongs to. There exists a zero function g minus 1 to R such that x comma 0 for all x belongs to minus 1 so on. There exists a C1 function g from minus 1 to 1 to R such that f of x comma gx equal to 0 for all x belongs to minus 1 comma 1. There exists a C1 function g from minus 1 to 1 to uh, 0 for all x belongs to minus 1 comma 1. There exists a C1 function g 0 infinity to R such that h of gy comma is equal to 0 for all y belongs to 0 infinity. Here exists a C1 function g from minus infinity to 0 to R such that h is gy comma y is equal to 0 for all y belongs to minus infinity comma 0. So basically total there 6 options, and out of those we need to understand which one is true and which is not. Okay, so let's look into it one by one. Okay, one. So let me know answer first. Only B, F, got it. And of course rest of them false. Solid. So for A, B, C, D, f of x comma gx equal to 0. This happens if and only if gx whole square is equal to 1 minus x square. And a solution exists only if mod x is equal to 1. Friend, f of x comma gx equal to 0 if and only if gx is equal to 1 minus x square. Okay. And this tells that two solutions gx equal to 1 root over minus x square, and these two functions are c1 and only minus 1. Okay. And for EFG, h of x comma gx equal to 0 if and only gx square is equal to x cube. And solution exists if and only x is equal to 0. And also h of g of y is equal to 0 if and only g of y cube is equal to y square. This conveys are uniquely for all y belongs to R. G of y divided by y. So if we delete 0, then it will be continuous. Okay. So this is the thing. So basically this is what this is an basically a use case of what use case of Mendele's theorem. Okay. So these are use case of Mendele's theorem and some other basic things. Okay. So there is really nothing to worry about. So now let's this objective question portion done. Now let's go for the subjective part. Okay. Oh well. Now let's start the objective question. Sorry, subjective question. Subjective. Okay. Question one. For 1 less than or less than infinity, the xn be a sequence in n such that mod xn p is equal to 1 for all n. Suppose xn I goes to xi for all n, and let x equal to x1, x2, xi such that p equal to 1. Prove that xn goes to x in n. Yeah. Now, and second part is that show that similar situation is not true for the supremum topology. So how to prove? So I mean we shall do the proof of p equal to 1, and this case is as similar way. Okay. Choose j further. Summation I greater than equal to j plus 1 makes I less than epsilon 4. Now choose n such that for all m greater than equal to n, and for I is equal to 1, j xm I minus xi less than epsilon by 4j. And it follows that summation I is equal to 1 to j semi less than equal to I equal to 1 j psi minus epsilon by 4 greater than equal to epsilon 2. Thus, for all m greater than equal to m, we have summation I greater than equal to j plus 1 mod xm I less than epsilon by 2. And therefore, summation I xm I minus xi, this thing equal to summation I is equal to 1 to j xm I minus xi, so I get equal to j plus 1 xm I by xi. This thing is less than equal to epsilon 4 I greater than j plus 1 xm I plus summation I greater than equal to j plus 1 xi and epsilon by 4 epsilon by 2 epsilon 4 left side of it. And corner B is take m is equal to 1 if m less than equal to n and 0 if m less than equal to n. And if we do this, then this problem solved. So basically we have solved this problem only for x equal to only p equal to 1 because for other situations the technique is quite similar. So what hmm. So I mean, so the same tech. So this is a technique only. Okay, there is nothing really complicated here. Okay. So now the next question. I hope this solution is understandable for everyone. If this problem, I mean, if you're unable to understand it, you can drop an email through the NPTEL forum. I shall get back to you by the email, or I shall get back to you by the next live session. Okay. Now, what? Well, the next question is, let V be a Banach space and let Vn be a sequence in V such that summation norm Vn finite. Show that there exists a V belongs to V such that V is the limit n infinity 1 to n I convergent. Hmm. Okay, so now solution. Since summation 1 to norm Vn is finite, so the sequence k is equal to 1 to n norm Vk. This sequence is Cauchy. Now summation 1 to n Vk was summation 1 to m Vk. This thing less than equal to mod summation 1 to n norm Vk minus summation 1 to n Vk, and so therefore the sequence Wn and Un is a Cauchy. Now the completeness of V Wn is convergent, and we have V is equal to limit n goes to infinity Wn, which is limit k going to infinity summation 1 to k I, which is summation 1 to infinity I. So basically what we have done, you have summation 1 to infinity of Vn is finite, so this gives the sequence of partials or norms. This is Cauchy. This tells that the summation 1 to n vk minus summation 1 to n vk, this is less than equal to finite. So there is the sequence wn is equal to 1 to n vk. So Cauchy, now the completeness of v wn is convergent, and we have the v is equal to limit angle vn and vi. Okay, that's all. Now question number, show that if v is a Banach space and t belongs to P of v, then norm t less than 1 plus minus t is an invertible operator. Invertible means there is an operator with whom I equal to compose identity minus t. This will become 0. Okay, so the solution. Well, just let me make it clear that these questions are not very difficult at all. If you try to understand this question, you can directly look at the solutions. But keep in one thing in mind that just look at the solution and just practice only one does not help. For the exam purpose, you have to practice a lot. Okay, so just make sure to make a sufficient amount of practice for getting a good marks in exam. Okay, because this certificate is very practically useful. Now, since norm t less than 1, so we have the convergent geometric series summation 0 to infinity norm k. Now since norm 0 to n t to the k, this thing less than equal to 0 to n equal to the k, it follows summation 0 to n t to the k is a consequence in BV, and let its limit be denoted by s. And applying lemma 1.5, we get identity minus t compose s is equal to identity minus t compose limit into infinity summation 0 to n t to the power k. This is equal to limit into infinity identity minus t compose k is equal to 0 to n t to the power n. This is equal to limit into infinity identity minus t plus 1. This is the identity. Similarly, you can show that F compose identity minus T is equal to identity. So this is the argument which tells that uh, the identity minus T is invertible. Okay. Now,
Can you repeat this part once again?
yeah,
This
sure,
question.
sure. So, mm, so, let me from the question itself. So V is the given Banach space and T is the bounded linear operator on V. Then, if the norm T is less than 1, we need to show that identity minus T is invertible operator. So norm T less than equal to 1. So, this means the geometric series summation 0 to infinity norm T to the power K is convergent. It follows that summation 0 to n T to the power K is a co-sequence in B. And let its limit denoted by S. Then applying one of the previous lemma, what we get? Identity T minus S equal to what? Identity minus T compose limit n tend to infinity 0 to n T to the power K. I mean, this is the trick here. Equal to limit n go to infinity identity minus T summation 0 to n, and if we apply this will go to 0. Okay. So that is the argument. Do you understand? Do you understand?
Yes, yes.
Oh, now let's go to the next question of it. Let V be a Banach space on BV cross BP. Take the norm defined by norm S of T is equal to norm is not T. And consider the function gap. So B of V to B of 1 be given by what? Given by f of st is equal to st. To show that f is differentiable and find its derivative. How to do this? Okay. So basically this is This technique is same as the previous one which we have solved in MCQ portion. The t goes to u square. Almost the same technique. Okay. So fix is t a b belongs to t of b and t belongs to k scalar. Okay. Then limit t goes to 0. F of s plus tf plus t of tb f of t by t. This is equal to 0 s of t tsb t plus t square ab by s of t. This is equal to limit s of b plus this plus t of t by t. And of course this is equal to s of b plus a of t. So this tells what? So this tells that a directional derivative of f in the direction of AB at the point ST. Therefore, so if at all f is differentiable at ST, then directional derivative of f at point ST continue operator eta given by AB goes to AB. So what we need to check? So what we need to check? So we need to check limit AB equals to 0 comma 0 norm of f of s plus a comma t plus b f of a t plus eta of a t pi b. This is equal to limit 0 norm ab and then the claim follows. Then the claim follows. Okay. Oh, well. So, so here also first we need to check the direction derivative exists or not. After all this, then we can check by using that checking the limit equals 0, we can say that the function is differentiable or not. Okay. So that's all. So now, well. So now, okay. So let's go for the next thing. So kindly wait. Well, kindly hold a minute. No, it's fine. Oh well. Now, uh, now let's go for the next objective assignment. Okay. The first question is the following: if R be a C1 function and P x naught y naught z naught, this says that if x naught y naught z naught equal to 0. Now consider the following statement. Statement 1. Here exists rho greater than 0 and a union C1 function g 0 with gx naught y naught z naught and gxy. Well, the question is that state whether the statement is true or false in each of the following cases. Option: f of x y z equal to x square plus y square minus 2x square is equal to 1 1 1. Option B, f x y z is 2x square minus y square. And z square equal to 1, 1, 1. Option C, f of x plus z is equal to x. So now, well, so huh. Now, so you are solving. Let me tell the answer. The option A be true, option false. The argument. The function h of xy is equal to x square y square takes the value to what at the point 1, 1. So we can choose rho greater than 0 such that h is positive in v1, 1 and put z equal to g of xy root over h of xy, which is smooth function in v1, 1. And it follows that f of x comma y comma g of x comma y is 0. And the same argument as in A, and C is as we were previous assignment, put g of x y plus minus root over x squared over y squared, which are definitely continuous, but of course not E1 in any neighborhood of 0, 0. Okay, so this is the thing. Now, why not? Now question number two. So true or false? Compact subsets of a topological space are always numbered. Closed. Now, singleton sets are, it is true, not, sorry, it's false. Since the singleton sets are always closed, but need not be closed sets. And if X be a Hausdorff space, then every compact subset is closed in X. Okay. Now, question three. I mean, really, I mean, there is nothing to explain. That's why I simply gave mark. Okay, there is nothing really. Which of the following are true for Q usual topology? First one, locally compact Hausdorff. Second one, Hausdorff. Fourth one, normal space. Think about it. So, question is that under which topology? I mean, Q with usual topology, which one is true? Okay, think about it. I shall get back to you after 2 or 3 minutes. owl. Well, so hmm, so which one was true? So solution B, then D. These two options only true. So let me explain. We have Q is equal to union and Qn. Okay, where Qn is an enumeration ENU of Q. Now each ifn Qn is a closed set, the empty integer. So Q is not. Second category. Now being Hausdorff, being Hausdorff, it is not locally compact, else will contradict the theorem. So Q is Hausdorff and normal space being a matrix space. Okay. Now let's go to the next question. One. Hmm. Let x is equal to 0, 1, 2, dot 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 and 0. Okay. With topology generated by the subbase 0, n belongs to n. Then n is a locally compact space. T1 space compact space is envelope space. So, solution. The option is D only correct. Option A false. Why? As for the element 1 belongs to X, the open set double 0, 1 containing it, there does not exist any open set of V or double 0, 1 containing N for which V bar subset of 0, 1. Option B. Why? Because as singleton 1 is not open and the closure of double 0, 1 containing 1 that is not contain. Option C. What is false? Since the open cover 0, 1 with n belongs to n does not finite circle. This is true for since